Hello, dear students and professors, sponsors and partners, friends and families. Thank you so much for taking your time of joining us here at our Hyperlaunch of Season 6. Hi, I'm Yasha, the CEO of Unzero Hyperloop.
And I am Aryan, the CEO of Unzero Hyperloop. And we are honored to have you at this stage, where today we can give you an insight into how a project like Hyperloop come into a reality here in Karlsruhe.
This project is powered by one thing: student energy. Students who decided to spend their time and expertise semester after semester. And now, after 6 years, we finally see the result of unwavering dedication.
So a big thank you goes to all our members and alumni for making this day happen.
What we want to create is a mode of transportation that is clean, efficient, and fast.
The Hyperloop is a revolutionary system. Where vehicles like metals travel in low pressure tubes, enabling contactless travel and a very highly efficient system.
This results in a system that is capable of reaching speeds of up to 900 kilometers an hour. What we know of transportation until now are railways, airways, roadways, and waterways.
Globally, transportation accounts for 27% of the total energy consumption of the world.
But how does it compare to the energy efficiency of a Hyperloop?
Airways with speed up to 900 kilometers per hour and energy consumption of 500 watts hour per passenger per kilometer.
Current railways with speeds of around 200 to 300 kilometers per hour and an energy consumption of only around 45 to 60 watt-hours per passenger kilometer.
And a Hyperloop with speeds up to 900 kilometers per hour and energy consumption of about 50 to 90 watt-hours per passenger per kilometer.
So this graph proves the Hyperloop's core principle, achieving the speed of commercial aviation and the energy efficiency of normal rail.
But where is all of this energy consumed?
The energy consumption of a Hyperloop can be separated into three factors. First, we have the tube, with the generation of a vacuum, the maintenance, and leakages. Secondly, we have the pod itself, with its levitation, acceleration, and powering all of the subsystems on the board. And thirdly, we have the infrastructure, which mainly consists of the tubes for the Hyperloops themselves.
In a study conducted at Unzero Hyperloop, we investigated potential railway corridors to look into if the Hyperloop line could be accommodated into it. The result was a study with identification of multiple corridors that could be used to implement Hyperloop line.
These range from a maximum of around 600 kilometers an hour on the Berlin-Prague route and speeds of around 1,000 kilometers max on the Milan-Rome corridor.
They were not only driven by the requirements of the project, but the engineering challenges to solve this project, where we want to create a zero-emission system which has the speed of aviation but the efficiency of today's railway system.
The history of Unzero Hyperloop began in 2020. Yes, this being during the corona pandemic. So you can imagine the people were running around wearing masks or working from home. And yet, a group of students decided to establish a club in Karlsruhe competing in the European Hyperloop Week, now the biggest Hyperloop competition in the world.
The first competition took place in Switzerland. Took place in the Netherlands first. The Netherlands was in 2021. The goal of the team was to create its own first prototype, including the levitating helium induction motor. The team started strong with the first newcomer award.
The second season took place in 2022 in the Netherlands, where the team developed multiple subsystems, such as a modular electronic system, high-voltage batteries, and a self-developed canvas protocol, with the team winning a total of 3 awards, including 2 research awards and the best electronic system
and safety. That this led to improvement and overall pod architecture, modular distributed control system, and an efficient propulsion system. During this season, we could secure ourselves the best guidance system.
During this season, we secured the Best Guidance System award. The fourth competition took place in Switzerland, Zurich. There, we integrated the moving truck system, one of my most iconic systems, and also displaying the strong collaborations we have with our industry partners, such as SEW Eurodrive. We're eliminating heavy onboard batteries and long charging times by charging our pod inductively through the rail in motion. We truly showed what we can do and achieve during that season by achieving the second place in the overall system category and winning the community as well as the scalability award.
In our last season, we made some further incremental improvements. We reduced the total pod weight and implemented some additional safety features, like the safety switches around the pod, as well as taking in the cooling system of our pod for the first time into the operation. We got placed third in the demonstration award and as well as fourth in the engineering design award.
And now about the season. The season started in September, and I think it's fair to say we had a rough start. With a limited budget and a small number of members, it was even hard to fill all of the teams we needed. So we spent our whole month fully focusing on a strict recruiting. You might have seen us at a couple of men's stands or in different fairs.
So be sure to join us to get a good start into season 7 through our onboarding, which will help you understand our system and give your own ideas of how a Hyperloop could do in season 7.
Through October and November, we also began testing our season 5 pod. We were testing the levitation and still had to tune the PAD control, which was not working on the first try, neither on the second or the third. But finally we had a levitating pod in front of us again. You can see how easy it is moving this thing, which weighs almost 300 kilograms with barely one hand. And it's really levitating. That really was the motivation that we needed to continue throughout the rest of the season.
After that success, we made the hard and influential decision to transfer the system into a new infrastructure. However, that meant taking all the parts, disassembling every single wire, and putting it into a new architecture.
And suddenly, we were left with an empty frame again. And we had to start assembling it up again, but we had the idea to create something much better and had the possibility to do that all the way through the process.
Aside from minor improvements, we also work on pneumatic braking system, cooling in vacuum, extension of the track, and as well as a new battery. You will hear more about this from our technicians themselves.
In February and March, we then assembled everything onto the new pod and mounted everything and redesigned all of the parts that we needed to integrate new systems that we integrated to fit it onto the pod perfectly.
And now we are here in June at the RDS, roughly 1 month before the competition. Now we have a fully assembled pod, but there is still a lot of testing to do. A month before the competition is really a very intense one.
So that was the history of the past seasons. So let's take a look what we did technically so far during that season. And it's best to hear that from our techniques themselves, because our technical teams are separated into 6 sub-teams. We have the electromagnetics team, electronics, software, cooling, track, and structure and packaging. So let's welcome with me our electromagnetics lead, Samuel.
Thank you, Arne and Yasha. Good evening, everyone. My name is Samuel, and together with my team, I am responsible for 3 crucial systems on our pod: levitation, guidance, and propulsion. Together, these systems enable the pod to move and remain stable in every spatial dimension we could think of. On our levitation and guidance units, we have made a number of improvements throughout the season. We have refined the control software, implemented grounded cables, and greatly improved stability, and especially reliability. Using distance sensors and a control system operating at 2 kHz, the electromagnets continuously adjust their magnetic force for smooth and cushioned operation. In a few seconds, I will show you a video of one of our levitation units on a test bench. Perhaps you have seen it outside already. The heavy on display. It will pull itself up and freely levitate. To professionally simulate a disruptive environment, we have chosen a hammer. You can see the PID controller directing the hammer hits in real time. The setting is quite smooth, making more rigid. The propulsion system is by far the most challenging part of the project. Our double-sided linear induction motor, or short LIM, generates thrust by creating a moving magnetic field which interacts with an aluminium rail beneath the pod. Throughout the season, we also made several major improvements. We've developed a whole new control software, introduced grounded cabling to reduce electromagnetic interference, and completely redesigned the motor wiring. By doing that, we have eliminated many stability issues and made the motor and inverter system significantly more robust. Overall, this season involved a number of challenges, particularly on the propulsion side. Thanks to the work of many people, we were able to solve them and significantly improve the overall system. Thank you. Let's welcome my teammate Anwar, telling you more about cooling to the stage.
Thank you, Samuel. Good evening, everyone. My name is Anwar, and I'm responsible for the thermal management systems on our phone. Samuel mentioned the levitation and propulsion systems posing a significant challenge, but they brought along another major hurdle. Because these electromagnets are essentially dense flows of copper wire, they generate a great amount of heat during prolonged operation. Here, you can see the CAD designs of our 2 custom heat exchangers. On the left, the limit vertical cooler manages intense electrical loads required for propulsion. And on the right, the MLU Franklin cooler, named after a complex generator that can be used to maximize thermal contact area. Our biggest leap forward this season was the design of a latent heat storage. Because we can't exhaust heat into the vacuum of the tube, we essentially have to build a thermal management to carry the heat with us. The unit you see here will be entirely manufactured out of aluminum, featuring internal channels for coolant flow. Despite all the advanced electronics of the pod, our exchange material is incredibly simple. It's just a mixture of crushed ice and water. And as they use to generate heat, all coolant flows through those channels, and instead of the magnets heating up, all of the thermal energy is consumed by relatively ice inside. Finally, to prove all of this wasn't just a theory, we conducted a thermal simulation using pulse. What are you watching here is a 15-minute time-lapse of our phase change material melting. And as you can see, by the end of the 15 minutes, the ice hasn't fully melted. This is because we deliberately designed the system with a safety margin to ensure reliability under any conditions. Thank you, and please welcome our electronics team lead, Vivian.
Thank you, everyone, and welcome to all. I'm David. This is electronics team. Basically, the electronics are a nervous system, connecting every component to each other. Without us, nothing moves, nothing reacts, and nothing communicates. In total, we have 12 PCBs on our board. Let's get the basics of the main ones. Armor fireboard. Through the laser, in total we have 5 of these. Through the laser distance sensors, we can power, we adjust the power accordingly, going to the electromagnets so we can power our guidance and navigation system. Then we have 2 PDUs. One of them runs on 24 volts and the other one runs on 12 volts. Our 24 volt PDU powers our shutdown circuit and our cooling pump. Then it also powers our 12 volt PDU through a step-down converter. Our 12 volt PDU powers our PCBs and our sensors, which helps us get real-time readings. Our input gets current, voltage, and temperature data, making us sure whether our system is working properly and within the safety limits. Our communications board handles all the data exchange between our PCBs through the 10-0 network. And finally, our linear induction motor board. It controls linear induction motor, which helps us to propel and brake properly. Okay, now we got the basics, but how do we connect them all? As Richard previously mentioned, our main power source is a neutron system from ACW to a drive. What a neutron system does is, it transfers power from that state through electromagnetic induction. No cables in between the pod and the track, which means no physical connection to slow us down. Through the pickups, we supply 48 volts to the pod. That 48 volts powers our electromagnets for levitation and guidance, as previously mentioned. That 48 volts also powers our electronics, but before it gets there, we step it down to 24 volts, so we can power our 24 volt PDU, which feeds the STC, our shutdown circuit, and our cooling pump. Then we step it down to 12 volts again, so we can power our PCBs, so we can get sensor data and control PCBs, microcontrollers, and sensors, which are the brain and the core. So, you may ask, is this safe? What about safety? We have a dedicated non-programmable shutdown circuit which runs through every PCB on the board. If any fault is detected, it cuts all the power automatically. We also have 5 shutdown buttons all around the board so we can kill the power manually as well. There's 2 track limit switches. If the board gets too close to the ends, it kills the power, so we can be sure it's not going to kill anyone. For us, safety is not optional. It is the foundation that everything else is built on. So, you may be asking, these are nice, but what is it doing this season? First of all, we got new temperature sensors for our linear induction motor board through cabin training. Improving cabin monitors our thermal behavior in real time. Second of all, we redesigned our communications board for better compactness, reliability, and stability. And one of the most interesting challenges this season was invisible, EMI, electromagnetic interference. Our cables were running to the electromagnets, and our sensors were behaving like an ungrounded radio station, radiating nodes that corrupt our sensor signals and destabilize the location. We found the cause. To fix that is shielding and grounding those cables. If any of this sounds like a challenge that's just calling you, PCB design, power systems, safety architecture, we're always looking for people who want to get their hands dirty. Electronics is where theory meets reality and someone has to make it work. With the help of coding and software, electronics gets complete. So now I would like to invite the software lead on show.
Our board now is a highly complex distributed
automated our communication layer, we built a centralized configuration system with the entire network architecture is defined in simple YAML files. This setup literally writes the networking code for us, ensuring every single node speaks the exact same language and completely eliminating human error. Furthermore, because trying custom physical hardware is generally frowned upon by our finance team, we have prioritized test benches this year. We engineer comprehensive mock testing environments for every single microcontroller. We can simulate sensor inputs, we can play with parameters and meticulously tune to get the absolute best performance. We essentially built the matrix for our microcontrollers, allowing us to relentlessly test our logic and brutally squash bugs long before the code ever meets the board. Finally, our mission control is as cool as the board itself. It not only shows the sensory readings, it runs the complete control of navigation, propulsion, and possibly every single variable with real-time telemetry, live data plotting, and a ridiculously sleek interface is essentially a SpaceX interface running on a laptop. Finally, but perhaps the most impressive part is that it's a little for the future, because this entire architecture is completely modular and automated, whether the next year's board has 11 microcontrollers or 100, this framework won't break us well. Overall, we didn't just write scripts this season, we built an entire software empire to keep this board flawless. But of course, the smartest board in the world still needs a track to run on. Ladies and gentlemen, please welcome the track lead, Ayane.
Rather than rebuilding it. That's exactly the approach we took this season. The track we built last year did its job really well. It was reliable, modular, safe, and provided all the interface in our thought we could operate. And even though the track isn't the subsystem that gets the most attention, it sets the foundation for everything else. Every acceleration run, every levitation test, every data we collect starts with a track that will work exactly fine. So instead of redesigning the entire system, we focused on the smaller improvements that would have the biggest improvement. One of those was our clamping system. Now I know clamps aren't the most exciting things to talk about, but when you're assembling and disassembling a track at competition, every minute counts. By redesigning the clamping system, we've set up faster, simpler, and a lot less painful for the team. The second major improvement was extending the track by 6 meters. 6 meters may not sound like much, but those extra 6 meters help us squeeze every bit of performance out of the Hyperloop pod. They give us more time to accelerate, more room, more opportunities to test our runs. And at the end of the day, what's engineering really about? Not building the most complicated solution. Not adding features just because we can, but finding the right solution for the problem in front of us. That's exactly what we did. We didn't reinvent the track, we tried to make it better this season. To show you how all these subsystems come together inside the pod, I'd like to welcome our structure and packaging team, Alisa.
So But here's the clever part. Instead of clamping, it pushes the pod downward, widening the gap between the magnets and the interface to demagnetize and slow it down. It's simple, it's elegant, and honestly, it's the kind of idea you only land on when you're forced to think differently. Then comes our frame. This is where it all comes to a full circle. Remember our problem? Season 5 was light, Season 4 was modular. We wanted both, so we stopped choosing. Our next frame is carbon fiber, slashing the weight while upholding every bit of that modularity. Light and adaptable, the best of both worlds already designed and ready to go. Our shell this season was made from natural fiber with an internal grip to keep it strong but light. With hours of amazing aerodynamic design built into it, we wanted more. So what's coming next takes us further. Sleeker shells, faster shells, and yes, I love cooler to look at. And here's the thing, none of this is just an idea, it's a blueprint. So when Season 7 takes over, they don't just inherit a pod, they inherit a roadmap. So if there's one thing that I want you to take away tonight, it's this. When you can't build everything, you build smarter. When you can't add more, you integrate better. And when resources run thin, you innovate harder. That's just not what we did this season, that's who we are. Now I'd like to invite Nick for the research demo.
Hey everyone, I'm Nick and I'm one of the research team members. So today I want to give you a quick summary of what we've been working on over the past few months. So, what we're trying to run is the Pareto optimization on a Hyperloop pod. Now I know the majority of you are probably confused, like what the hell did this guy actually say? Actually, it's very simple, and I would say borderline very cheap concept, which is jumping into fancy engineering words. To explain what Pareto optimization is, I'd actually like to give an example, which I think almost everyone in this room has gone through. So imagine this example, you're staring at a mountain of lectures for a class you actually haven't attended any lectures for. So you accept that you can't learn literally everything. So you spend 3 days mastering 80% of the content. But this is one really specific, weird subtopic that you see as a theme, and you're like, you know what, there's no way in hell the professor actually enhanced this. Famous afterwards. You go into the examination, you feel confident, you flip over the paper, and what do you see? You see first question where 40% of your grade explain the exact same concept that you skipped at the end. Now, the Pareto optimal theory is similar. It's the idea that you don't always need 100% effort for great results. It's the idea that 20% of your target effort can get you 80% of the outcome, whereas chasing the last 20% of perfection takes massive 80% of the energy. It's all about finding that sweet spot. Now, how does this relate to Hyperloop? Good question. So, what makes Hyperloop really efficient is that we run the pod in vacuum, so we have virtually no air resistance. But creating 100% in vacuum is well impossible, and even if we try to create as much of a vacuum as we can, it's going to have horrible energy efficiency. So, our research team was focused on finding that exact sweet spot where we have the least amount of vacuum running, while also having the least amount of air resistance. So our research team simulated the aerodynamics of the pod in the open flow, factored in the energy used by the vacuum pump, and ran it under different scenarios. And we plotted this table as a result. This basically shows us that the most energy efficient setup for a 400 kilometer trip occurs at a pressure of about 250 pascals, with the pod cruising at 800 kilometers per hour. To put that in perspective, 250 pascals is still super deep vacuum. It's less than 1% of the air we are in right now, but it's still much more easier and much more cost effective than running a complete vacuum. Now, beyond the numbers, why does this actually really matter to us right now? Is because for the longest time people have thought Hyperloop is this really cool sci-fi concept that's only going to exist in movie, or if it comes in real life, it's going to be insanely expensive. What our team did over the last few months was prove to you that you don't need impossible crazy tech to make this happen. All you need is just smart optimized engineering. It's a huge step forward, not just for our team, but Hyperloop in general, and I'm really proud of what we have achieved together as a team. Thank you, and now I'd like to introduce our host, Aaron Black, onto the stage. Thank you.
When you look at the pod, you see engineering, but behind it, there's a very crucial non-technical side. A year of planning to make sure the team has the resources, the visibility, and the structure it needs to perform. That is what operations is for. That is sponsoring, even management, finance, and marketing. And here is the operation team, who will now give you more insight.
for our active rebuilding the future of transport. But marketing is more than just sharing updates. It's also about creating an identity. One of our biggest projects this season was building the visual identity of the pod. We shared flyers, we shared business cards, brochures, banners, and merch. Will you guys give the audience a tour, please? We made sure to capture all of the movements of our technical members who work very hard by sharing photos and silly videos that they sometimes try to avoid. But it was all for the very good, of course, exposure. And by consistently sharing their story and showcasing their work, we managed to strengthen Museum's reputation as Germany's only Hyperloop team. And now I'd like to welcome back our hosts, Arya and Yasha.
Introducing the Season 6 ball, Orca. Now we would like to invite 5 members